So the question that just got asked is like, how did I find myself like working on formal verification and like, what brought me to this interest? And that it is kind of beginning with this story of, at my first job, I was like writing some C++ code. When I was writing that code, I would get these like software crashes, something called a segmentation fault, which is a particularly nasty type of error that C++ and other languages in that cluster, in that family, can exhibit. And what's nasty about them in particular is that they're not great at, by default, giving you a lot of error information about why it crashed. It just says, I crashed, figure it out. And so when I was going through that, I finally figured out, like after 2 days, like burning, up to 3 a.m. nights, like was just having issues with this. And then when I figured out what it was, the issue is that I used parentheses instead of brackets. And what's really annoying about that is that like both of them meant something in the language, right? So if I try to allocate a new array of like 3 elements, then I will use brackets. And if I tried to allocate a single integer and initialize it to the number 3, I might use parentheses. So both of these lines of code have legitimate interpretable meanings in the programming language. But the difference between them is so stark that the language, it is strange that it allowed me to substitute one expression for the other, right? Like it shouldn't be, intuitively it shouldn't be the case. It'd be like if I replaced, an adverb with like an adjective in a sentence. Like you kind of look at that and you're like, that doesn't seem right. So at that time, I was like, okay, I needed to figure out a better way to go about software development in general. And I remembered kind of in the very, very back of my head that like one of my friends like had mentioned that every time he wrote like Haskell code, that like if he got it past the compiler, then it would just do the thing that he expected it to do. And like my senior year of college, I also remember like Rust had just hit like 0.12, and so it was like kind of starting to be useful, and people were experimenting with writing operating systems in Rust instead of C. And then Rust had a whole like cluster of I was about to say traits, but that's like a really poor use of that term in context. It had a cluster of properties about it that made it such that programs that misbehaved in certain ways, you just fundamentally couldn't write them and get the compiler to accept them. And so around that time, I was trying to seek for better tools that would reject programs that fundamentally didn't make sense. And so this was like in 2017, I picked up Haskell that year and started playing with that sort of more and more and more. And what's interesting about Haskell is that you kind of go through and learn, when you study software engineering or like computer science, kind of in your early years, you might get told a lot that like all programming languages are more or less the same. They vary a little bit at the margins, but they're mostly like all the same thing. And that's like actually not true. It's just that there are several clusters of programming languages where the differences between the languages within a cluster are quite small, but like between the clusters is actually quite large. And so things like C++, Rust, C, and then like if you're willing to bend definitions like Java, C#, and like beyond, they're all kind of in a cluster. Like maybe Java and C# are like a little further away from like Rust, C++, C. And then you have like over here, you've got your like Python, Ruby, JavaScript in that set. And then because they're like interpreted instead of compiled. And then you've got stuff like Haskell, Standard ML, OCaml, Scala in like a different cluster completely. Those languages will, even if you know C, C++, and JavaScript like backwards and forwards, like your Haskell, Standard ML, those are going to feel like alien languages. Like not just in that the syntax is unfamiliar, But the same way that like, if I was to make an analogy to human language, in English, we don't have this notion of like the pitch of our voice changing the semantics of the language, the way that like Mandarin or Cantonese do. So if you like are speaking Mandarin or Cantonese, like if you say the same syllable with a different intonation, it's not just that it has a different connotation the way that it might in English, because we raise our pitch to indicate questions or to like indicate some sort of emotive aspect of the language using tone. In Mandarin or in like Cantonese, those the actual meaning of the words that you say change based off of intonation. And that's like just not a concept that is like remotely present in English. And that's kind of the level of difference that I'm talking about here, which is that there are things happening in these more alien languages that are so different from your typical programming languages that you learn in an undergraduate degree, and that sort of learning you're almost learning to program from scratch again. And so you might ask the questions like, well, why do this at all? Like, if it's what is the benefit of it being so alien? Because unlike human languages, which kind of evolved from just like culture and like experimentation and whatnot, and so there's many different paths towards making a language like that. Like computer languages are a lot more designed, and we can talk to the designers of other languages. And so every way that a programming language behaves, like it has a reason behind it. And the thing about programming languages such as Haskell is that its design choices are around trying to make the language all like very uniform, so that every part of the language kind of behaves in a predictable way, and it all can be put together, like snapped together in a common interface, like the way that you might have like Legos or, you know, a modular synth or something like that. But as a result, it also kind of puts you in a straitjacket. And because like the same way that like, okay, these Legos have a common interface, so you can plug them into each other in a bunch of different ways, but like there's only one sort of class of ways to plug them into each other. And so when like the language then enforces this thing like called type that's like known as type safety, which is that in programming languages such as C, C++, et cetera, you might have a bunch of basic types like integers, strings, characters, those sorts of things. But in languages, and then you can sort of define your own types on top of that, where you might say, okay, like I want to have this notion of, I don't know, like an essay, and an essay is like 3 paragraphs, and every paragraph is like 5 sentences, and you can like enforce this like heavy structure.
Another good example of that is oftentimes in languages that are less rigorous in their type safety, you can run the hazard of doing things like adding the number 1 to the letter 1, and now you get 11 instead of 2. And other times you wind up with something, I call it stringitis, where everything's just a string. Mm-hmm. So you have an email is a string, and an image is a string, and a URL is a string, and it's just like everything's a string, and it's just terrible. And so
yeah, and so like my dad had this joke when I was growing up that like he would be like, he'd jokingly ask like, what's the circumference of a chicken, right? And it's like it's a strange question, right? Like because like we know as humans is like, well, circumferences are things that apply to like circles. Maybe a sphere if you're like really like pushing it.
Assume
like,
a spherical chicken.
Yeah, so if you assume a spherical chicken, you can ask what its circumference is. But the point being is that like there are certain questions or certain statements that you can say that are not just wrong, but they're like incoherent, right? So I could make the statement that like this water is hot, and that might be a false claim, but it's not an incoherent one. Like when I say this water is hot, you know what I'm attempting to say. But even if you know that what I'm attempting to say is not actually true. Whereas if I ask what's the circumference of a chicken, like that's an incoherent statement. Like it doesn't even make sense like what is being asked.
I mean, technically, if the water is liquid, it's a lot hotter than absolute zero.
Sure, and so like to that point, like you might be able to debate the truth claims even in like ambiguous scenarios, and that actually will segue later. Is like sometimes you don't know whether something's true or not, right? Like if I say this water is hot, it's like, well, hot compared to what? So like sometimes you need to refine these statements about whether or not something, like, so that you know what's actually being said. But like I said, it's at least coherent. And so what Haskell allows you to do is it allows you to be like it was the first time I had this experience of being able to be like almost arbitrarily specific about what I was trying to get the software to do.
Arbitrarily specific almost sounds like a contradiction, like an oxymoronic.
Well, the point being, it's like, okay, I could define, it's a good observation. When I say arbitrarily specific, it's that if I'm coding in C, data types are a number of different things, and they're mostly set in stone. Yeah, you can sort of type def on top of that, but for the most part, you only like have product types. And then if I want to have this notion of like like let's say that like I want to be able to define the concept of a car, and a car could be an SUV, a pickup truck, a sedan. Maybe I want to generalize that and say like actually I don't even want just a car, I want a vehicle, and so I want to be able to add on top of that motorcycle, boat, and like maybe a whole different class of boats or like airplanes and stuff like that. It's that I want to have this ability to say like this data type is A or B in addition to other data types which might be like A and B, where the and being like a car is 4 wheels and a transmission and doors and a steering wheel, etc. And so the being able to play with this this combination of like ors and ands ended up feeling like I could almost sculpt the data to exactly the problem domain I was working on. And this became important because if you can't do that, then as the representation of the ideas that you have diverge from the reality of those ideas, that's where all the bugs hide in software. And so to the extent that you could make the language that you used to talk about the concepts that you're working in match exactly those concepts, then a lot of times the bugs, there would be no surface area for bugs to pop up, because all bugs are when the map stops matching the territory.
And that's why you started the conversation kind of around the concept of it being able to express intent.
Yeah. And so one of the sort of big eye-opening moments I had from moving from like C, or like C++ to Haskell, was that I always felt like when I was coding in C++, that the data types that I was defining existed to serve the computer. Whereas when I moved to Haskell, that was the first time I had the experience of, oh, I can make the data types match the way that I think about this, and only incidentally be something that like the computer understands. Now, the trouble is, though, is that as I progressed on this journey, like using Haskell, even Haskell isn't enough to like really get everything that you want, because you might be able to say like, oh, I can define a list, like a list data type that's agnostic over whether it's a list of numbers, maybe it's over a list of strings, over a list of cars, a list of vehicles, to use the earlier concepts. I might be able to define that list, but then the second that I want to say like, oh, this list always has somewhere between 5 and 10 elements in it, I can't actually put that requirement or that invariant into the language itself. And so that meant that anytime I wrote a function that expected that behavior, I'd have to then first check, is it at least 5 elements, and is it no more than 10 elements? And if it happened to be outside of those bounds, I'd have to throw errors, and then like all sorts of undefined behavior happens, and then I don't know what the software will do in those conditions anymore.
I can relate to that as somebody who's been writing Rust for 8 years. I mean, we have ownership types famously, we have generics, we have associative types, we have sum and product types, we have all sorts of fun little, even const generics in different combinations, right? But there's definitely limitations to the expressiveness of the type system that, like, when you're working in Lean 4, like something that is very firmly rooted in dependent types, and like dependent types are kind of like an interesting unlock. How you could basically express even things like linear types and affine types and other higher kind of types kind of like through dependent types.
I don't know if that's true, but I truly don't know.
Oh, well, maybe not fully. You can approximate their effect, basically.
There are a lot of things that you can do. Dependent types are very special in that you can, I think maybe it's useful to rewind here. So what's happening here is that we have type systems that that are progressively getting more and more like malleable. Like we can like sculpt them exactly the way that we want. And, or there's an ordering to these things, right? So some of them are very inexpressive. Like, you know, if we want to take the worst example, if you have your JavaScripts and your Pythons of the world, right? Where there's nothing, right? You have no guarantees about any of the data that you're working over, and you kind of just have to cross your fingers or implement a bunch of runtime checks in every function, or have a test suite that's like 10,000 tests long or whatever, in order to get the same level of assurance.
More lines of code in your tests than you have in the actual implementation.
Yeah, and then you might have a step up from that where you have your like C, C++, Java, like that cluster where it's like, okay, I have basic data types and I can rule out large classes of bugs, you know, statically in the type system, and that helps a lot, but it still leaves some to be desired. And then you have your next class, which is like you know you've got Rust, which is like very, very good, like a massive improvement over the C++ cluster. And then you've got like your SML, OCaml, Scala, Haskell cluster, which is like a small improvement over Rust. And then, but even then, like it's like there's still stuff out there that I want to be able to say that I can't quite say. And so when you cross over from that into dependent type theory, it feels like all of a sudden everything that you want to say is something that you can say. And the important part about this is like, well, why do we care about this at all? And it's that when we are trying to write code, we're writing, we throw the term logic around a lot, but this logic is this sequence of connectives of like, okay, I have this thing, I want to be able to say like A and B, I also want to be able to say A or B, I also want to be able to say, well, like, if A is true, then that implies that B is true. There's like a whole bunch of like logical connectives that allow us to reason about, which is like be able to make inferences and truth claims or evaluate the truth of certain statements. And when we have that ability, we kind of know with more certainty whether or not we're A, agreeing on the same things, and then B, whether or not those things are true. And it happens to be that there is a formal equivalence. This is something called the Curry-Howard isomorphism, which is that there is a formal equivalence between functional programming and formal logic. And that means that any logical statement that you can make, for instance, there will never be more than 21 million Bitcoin. That's like that is a truth claim, right? Whether or not it's true is like, going to be subject to a whole bunch of proofs and whatnot, but the point is that that is a statement that can be made. And what's cool is that because of this equivalence is that can be translated into a functional programming construct. Now, what's interesting about that isomorphism is that there's different, I talked about these different clusters of languages that, different elements of the logical language they come online, right? So there's this notion of and. Almost every programming language has a notion of and. At the Boolean level for sure, but even at the type level, like almost every programming language, including JavaScript, has a notion of product types, and which is to basically say like A and B. They're known as objects in JavaScript. Structs in C++, Rust, etc. But that's this idea of like, I have this data and I have this data, and I'm essentially like gluing them together in this like sort of joint piece of data. Then, okay, so we have and, now we want to be able to say like, okay, I want or, and this is where like sum types start to come in, and this is like, summing, like to add together. And when those come online, then you can start to make statements with ors. And it turns out that if you have and or, almost every different shape of data can now be expressed. But then you have certain things like, well, if I have...
By the way, some types are often known as, so you have structs as product types. Some types are like tuples or...
No.
No?
Tuples are also product types.
Product types, okay, then what about...
variants or unions, or those are like the sort of friendly names for...
What would be the Rust equivalent then?
Enums?
Enums, yes, enums, enumerated types, yes, okay, yeah. So like an or, right? It's any one of these, right?
Yes.
Enumerated members, okay, cool.
And it's actually funny that this like product and sum type actually have these like mathematical equivalences, which is that the number of inhabitants of a product type is the product of the inhabitants of its individual components. So if I have, two Booleans for say, it's like a Boolean is a type that has two possible values, right? It is false and true. And if I have a product type, which is, the simplest product type is a pair. So if I have a pair of two Booleans and I join them together, that data type overall can have 4 different states. And this is probably not the best example because the sum of 2 and 2 is also the same as the product of 2 and 2. But
well, it's kind of funny there also is, in that comparison of a Boolean type, is that you can't really have that's very firmly a sum type, like an enumerated type, because there's no such thing as like something that is both true and false.
Correct. Yeah. So data types only ever take on the value of one of the possible things that it could. So you could think of the types as the set of possible values, and the actual value that takes it on is it's like one of those possible, is one of the members of that set. Now, what ends up starting to get interesting is that, like, okay, well, now if we want to talk about implication, it's like, well, if X, then Y. Like, yes, we have if statements in every programming language, but sometimes we want to be able to say that at the type level because we want to be able to exclude the possibility of this result type if we don't have the argument type. And so that's when like functions start to come into play. It's like, well, if I have a function from A to B, then if I can produce a value of type A, then I can feed it to this function and get a value of type B. And so if you wanted to then start to tie that into like logic, it's like, well, if I have this statement of, if I drink water, I will not be thirsty, right? That's a statement on its own. That does not mean that I will not be thirsty anymore. But it does mean that if I have something that witnesses this idea of having water, that now that together with this implication statement can be combined to a combined witness of I will not be thirsty. So all of this is just like really, really in the weeds of saying that like when we have all of formal logic available to us, we can start to talk about any arbitrary claim we want to, or any arbitrary claim we want to make about a system can then be expressed in this way. And then what's cool is that when we talked about before this idea that there are sets of these types, which are sets of possible values, and then there are values that are members of that set, through this isomorphism I mentioned earlier, one of the things is that the types function as propositions, basically a truth claim, and the program that implements that type is its proof. And so it turns out that if you can come up with any value at all that inhabits that type, it means that you've proven that claim. So when you have all of formal logic available to you to be able to be expressed as these propositions, and you have this equivalence, then you can then start to prove all of those truth claims that I was talking about. So one example of it might be there will be no more than 21 million Bitcoin. Now, I might ask you the question, like, because I do want to tie this back to Bitcoin because we've been pretty far in the weeds about like logical systems so far. Like, everybody in this room has a vested interest in this idea that there are no more than 21 million Bitcoin. But if I were to ask you, like, how do you know? Like, do you think that you could answer that? Right, but do you, why 21 million? Like, do you know? Yeah, so where does that come from? Yeah. That summation equation is interesting, but do you
Yeah, so it's like you start with 50 and then like every 2016 halvings or then it turns into 25, it cuts in half.
Yes.
And then like,
Yes.
and then at some point you can't cut it in half anymore and so it must end. And so you have 20 less than 21 million.
Okay. Where in the code is that summation equation?
Is it in consensus.cpp?
It's nowhere. It's a derived property. So this is the thing, is that the notion, the fact that there will be no more than 21 million Bitcoin is not something that's written into the code directly. It's something that you know to be true about the code based off of a whole bunch of other things in it. It's the difference between, like, if I said, I'm kind of like at a loss for like a good analogy here, but
Is it so much the difference that a mathematical equation isn't necessarily a code, but a mathematical equation underpins coding?
it's the other way around actually in this case, which is that the mathematical equation that, why am I blanking on your name? Sam? Okay. That Sam had mentioned is not in the code anywhere, but it is something that you can construct based off of the code that is in Bitcoin. And so the question then is, like, okay, if I wanted to make the statement there are no more than 21 million Bitcoin, one of the arguments I might give for that is that summation equation, exactly the way that I asked you, right? Like, I was like, how do you know? And you're like, the summation equation. And I was like, great. Where does the summation equation come from? That itself has roots in other aspects of Bitcoin. And so the issue is that, like, if you follow the sort of the architecture of Bitcoin's like soundness all the way to the bottom, it ends up being like these tiny, tiny little things that all like kind of stack up together in, I don't want to say a house of cards because that implies a fragility that's not really there, but like, yeah, it's like you built together, yeah, you.
That looks like the summation equation.
Yeah, you would make
And then you would say that you can like reduce all of this code down to a type that fits the summation equation.
Yeah, that's more or less what's going on here. Now, what's really cool about all this is that if you can do that, and then you can then put the proof together, that sort of like proves that because this type is a very sort of Haskell and below way of looking at things. But when we start talking about like Lean4 or Coq or Isabelle or like any of the other proof assistants, they generalize this notion of a type to like this like universe hierarchy. But at the bottom of the universe hierarchy is a proposition. And the proposition, when it is inhabited, means that you've proven that proposition. And so you might make the proposition of there are no more than 21, for all possible chain histories of Bitcoin, like you're quantifying over every possible way anyone could use Bitcoin ever, right? Not just all the ways that it has been or all the ways we could imagine it to, but like all possible ones, period, that there will never be more than 21 million Bitcoin. Like, that's a very strong claim to make, and it's a very useful one at that, right? Because you don't just want to know that there's only 21 million Bitcoin now. You don't know that there's just 21 million if we use it in these particular ways. Like, you want to know that for any possible chain history that claim is going to hold. And when you start to do that, you can't use traditional software testing methods anymore. So you formulate that statement as this proposition, which is a type, and then you provide a value of that type, and that essentially is the proof. So this is like a super useful thing to do, and you might ask the question like, okay, then why don't we do this for all of software? And the answer is because it's really fucking expensive. The number of people who know how to do this at all is vanishingly small. Of the people who know how to do it, it takes forever, right? Like, if you, it's the difference between, because I could ask you this question of like, you know that addition commutes. So A plus B equals B plus A, right? Everyone kind of learns that in elementary school. We kind of take it as truth. But like, why, like, how do you know that's true? Like, could you prove that that's true? And like, if you were to prove that that's true, what axioms might that rest on? Because all proof systems require you to just take these like kernels of truth as like axiom at the bottom, right? You just assume them to be true. And then if enough people look at an axiom and be like, yeah, that's like a reasonable axiom to start with, then you can start to build up all of the different truths that you can derive from those axioms. So you have this like commutativity question, like, well, can you prove that? It's like, it turns out that the proof of that claim is pretty laborious. Like I have done it by hand, and it is not like the most straightforward thing in the world. Like even now, having done it before, like I don't know that I know like, you know, chapter and verse of like exactly how that proof goes together. So, and that's a pretty mundane claim, and in that category of like things that you could prove, it's actually a relatively straightforward one to prove. So when you start to get to much more complicated things like, okay, prove the security of this cryptographic protocol under this adversarial model, right? Like that explodes in complexity in terms of like how you might try to accomplish that. So really, really expensive because the expertise requires a lot of training. A lot of people don't have the patience for it. And then even for the people who do, it just takes forever to do. But this is where LLMs have become super interesting, because it turns out that for the most part, like with the exception of like certain types of mathematical curiosity, all proofs of the same claim are equivalent. So it actually doesn't matter if you can prove a proposition like 4 different ways, which one you choose actually just doesn't matter. You just care that the thing is true and that it's provably true.
Question about that. Would you then say that like maybe a claim that is verifiable with Z3 using SMT solvers is like also, like if you can also do it prove the same claim using Lean 4 and dependent types, that they're equivalent?
If you can prove something in Z3, then you can prove it in Lean 4. The reverse is not true. And the reason is that things like Z3 and SMT solvers require decidability. It requires that you can exhaust the search space. The issue is that some claims, so one that's I think particularly interesting to this room here is that everyone's probably in here has probably heard of the Nash equilibrium, right? The thing that won John Nash the Nobel Prize in Economics is that he asserted that for all finite games, there exists a Nash equilibrium in that game. But if you look at the proof of that claim, it appeals to the Brouwer fixed point theorem from algebraic topology, which is a non-constructive argument, which means that you could not actually express that proof in something like Z3 because it's not relying on exhausting a search space and saying, hey, like here's like the actual assertion that like actually proves the claim. It's saying, it kind of inverts the premise. It's saying like by contradiction, like it would be impossible for this not to be true, which is very different than saying like, here's the thing that says that it's true. And so like there's like classical logic, I think that all of that rests on like this sub branch of logic that's called classical logic, which gives you the law of excluded middle, which says that there's every claim is either true or false. There's no third possibility about whether or not a claim is true, right? It either is or it isn't. And it turns out that that ends up being a really important strategy for proving things, because sometimes you might be like, well, okay, I want to prove that this is true. So let's start by assuming that it isn't and show that as like self-defeating. It doesn't actually like directly prove the thing. It's a roundabout way of proving it. And you can do stuff like that in Lean 4. You cannot do that stuff in Z3.
Right, it has to be either satisfiable or it'll tell you it's unsatisfiable, right?
The only way to assert unsatisfiability in Z3 is to exhaust the search space, and that still requires the decidability of the problem at all, right? Not all propositions that you can prove to be true, can you do it via decision procedures?
Which then, of course, goes back to like the eternal question of completeness versus consistency.
Can you explain further what you mean?
Like in Gödel's incompleteness theorem, there are technically two, but he explains that you can't have both, right? A complete
Correct.
system and also a consistent system that doesn't. There's no place where it would contradict itself.
That's correct.
And so, essentially,
But that doesn't depend on decidability at all.
right? That's a different dimension.
Yeah.
But they're kind of complementary and kind of do
Yeah, no, and in many ways, like the undecidability of the halting problem that Turing discovered in 1933, that won him, well, I didn't win him the Turing Award. It was named after him, right? But like that was his like major contribution to computer science. That idea is spiritually Gödel's third incompleteness theorem, right? So like I think at the turn of the century, David Hilbert had like these like three main problems of like the question of like, is mathematics consistent? Is it complete? And is it decidable, right? And so completeness is like, are all true statements provable from the axioms? Consistency is, is it the case that no false statement contains is provable? And then decidability is, for all possible claims that you could make, is there a procedure that can decide whether or not the claim is true or is false?
within a human timescale, ideally.
Yeah, it doesn't require the traditional notions of efficiency that we have in computer science, like polynomial
Well, the halting
time.
problem
Yeah.
adds that dynamic.
But undecidability is like this idea, like, is there a uniform procedure? Like, I can write a single program that will deterministically sort these claims into true or false, always. And it,
Go back to Bitcoin though a bit. So like, say maybe like an axiom would be like EDSA is valid or like is unvalid.
no, we'd start below that actually.
Yeah, but like maybe you would start at that point, or you would say like SHA-256 is like impossible to like guess.
Yeah, so
There's no like two pieces of data that can hash to the same thing.
yeah,
Like pre-image resistance versus second pre-image
Prove
resistance.
going up from those two axioms, or you can start from below and you're saying I'm going to prove SHA-256 and then I'll prove EDSA, and then once I have those proofs, then I can go further up.
yeah, and it turns out that let's talk about SHA-256 for a second, because almost all of Bitcoin's security hangs on the collision resistance of SHA-256, right? This idea that no two distinct values hash to the same hash. We depend on that very heavily. Like proof of works security depends on that. Any and all questions of malleability that you might see in protocol discussions are actually that. And it turns out that on its own we kind of have to take it as axiom, because technically speaking, it's false. Because there is an infinite number of inputs to SHA-256 and a finite number of outputs. And so by the pigeonhole principle, which is like this thing in mathematics where it's like if you have a certain number of buckets, then in order for you, if you have one more than the number of buckets of things, then, and you wanted to put all of the things in buckets, then at least one of the buckets will have more than one thing. There's literally an infinite number of sequences of bytes. And there's a finite number of distinct hashes. And so there has to be a collision somewhere. So as a claim on its own, it's false. But we assume that it's hard to find, and so we take as axiom in this case that it's not, that those two things are not true. And if we can prove the security of the overall thing based off of that axiom, then we just are depending on the fact that it's so hard to find one of these collisions that we can't break the security of the overall thing, because we can't break the collision resistance of the hash function.
Well, that also reminds me a bit of like the question of pre-image resistance versus second pre-image resistance, and why like people do like tagged hashes like on either end, or SHA-256D like twice, right? Because like SHA-2 does have a limitation where if you're able to add additional data, you can maybe potentially arrive at a collision through what they call length extension attacks. And
right, and it's the double SHA-256 actually. I learned this last week. Because I always like kind of scratched my head. I was like, why do we SHA like 256 things twice? Like, isn't one sufficient if we're assuming collision resistance? And it's actually that, because there's a certain underlying structure of the state folding function within SHA-256 that depends, or that can be exploited by this length extension attack, where you can kind of predict the internal state of the function.
the Merkle-Damgard construction. Yeah. And what's also interesting is the tagged hashes are another way to do it, only once instead of twice, but you need to add basically some fixed data to the beginning and the end. So a good example of this is HMAC 512, where they use SHA-2, SHA-512, but then they add additional data to either end of it so that it is essentially, it does have that second pre-image resistance.
So anyway, all of this is to say that, this is a technique that is really, really powerful in order to be able to provide like highly, highly certain guarantees, but it was hitherto very, very, very expensive to execute. Now, with the advent of LLMs, we can now make the propositional statement. Humans can write the propositional statement that we care about. There are no more than 21 billion Bitcoin. And then we could say, go forth, LLMs, and prove this claim. And it doesn't matter how they prove it, because the Lean 4 kernel is like very, very well like engineered to like only sort of apply these logical rules in a very, very, it's like, I think the total size of the Lean 4 kernel is something like 5,000 lines of code. Like, that's a very tractable amount of code for a human to read.
Oh, but that's not the size of Lean 4.
But it's the size of the Lean 4 kernel, which is the thing that validates the proofs.
For sure. It's just, Lean 4 is famously self-hosted, and it was a monumental amount of effort that, like, when you go to clone that repo, it's like gigabytes of a bunch of all the work they're going through to arrive at literally a self-hosted, dependent type compilers, almost a bit of like a monumental achievement, I think.
I mean, self-hosting of any compiler is a monumental achievement.
For sure, but one that...
Guiding the LLM in any sort of way, or are you just setting it out to like go? It's not brute forcing the problem.
So it actually, well, you're right. It's not quite brute forcing, but it also kind of is. So the way that modern LLMs write code is that it will just kind of like vibe out its first draft. It'll run it through the compiler. The compiler will give it feedback, and then it will use that feedback to decide, okay, what's the next, how do I need to tweak what is there in order for me to get to like a better state. And eventually when the whole thing passes the compiler check, then it says, cool, we're good to go. And so it's kind of guiding itself in that way. Now, you're kind of guiding it in the sense that you're giving it the proposition to prove. You're essentially giving it the top level statement. Now, you can also get the LLM to write that, but that requires a much finer touch, a much higher level of expert judgment. But it is, until the advent of LLMs, the proving work in terms of the amount of developer time that it consumed dwarfed the specification work. So there's like the specification and the proof. You need both, and LLMs can kind of like eat the proof work for breakfast with basically no downsides. Actually, I want to make a stronger claim than that. I don't think there are any downsides. Now, the legibility of the proof, you may not get mathematical insight for why something is true. Like, you can look at the proof and it can be like really nasty and like I'd be like, I don't understand why this is the case. But you know that because it passes the Lean 4 kernel, that it is correct. So you might not derive insight, but you at least know it's true. The specification, if you let the LLM handle that, it's like it's very easy for you to get into situations where it vibes out a statement in the specification that subtly diverges from your intent, and then you get into all sorts of trouble because then this is where it's kind of a double-edged sword because you don't want to give yourself a false sense of security. You don't want to give yourself a false sense of security by saying, oh, it's provably true, and then like the thing that you proved is like not actually what you thought you wanted to prove.
Well, for one thing, LLM's really good at refactoring, so maybe once you've actually proved it, you can refactor it into a way where you can read it.
I'm glad that you said that because I literally did that like 2-3 weeks ago where I was looking at the proof for something, and I was like, I hate this proof. Why? And like I just asked the LLM, I was like, why do I hate this proof? And it's like, well, there's a lot of repetition, and there are like, so the way that these statements that I'm talking about, these truth claims, they're just formally called theorems in Lean 4, but there are kind of many different types of theorems. They're like headline theorems. These are the things that you care about, like there are no more than 21 million Bitcoin. And then there are theorems that are kind of like mile markers on the way to that headline theorem. Those are called lemmas typically. And so you might want to take this giant proof and factor out lemmas, which the lemmas themselves are not interesting on their own. Like a human wouldn't be like blown away by looking at the truth of this claim, but it ends up being a useful tool in order to like construct this like very, this skyscraper of a logical structure.
A useful axiom here is make it exist first, then make it good.
Yeah, and so to that end, it's like, yeah, you look at the proof and you talk about like the refactoring. It's like that's the make it nice afterwards. But so when I posted to the Bitcoin Dev mailing list last week, I think it was last week, that I was like, yeah, if people care about proof legibility, I'll put some work into making it easier to like actually read the proofs so that humans can look at them. But for the most part, I don't anticipate that being a point of value contention. Like, I don't think that a lot of people are going to be like, this would be super valuable if only I could like read the proof. Like, maybe that'll come out, and if it does, like, I'll put work into it. But other than that, like, I'm much more interested in getting the logical structure of the Bitcoin protocol formalized at the specification level, and then just like vibing out the proof code.
Yeah, I mean, well, there's a lot more value in knowing that the approach is correct than just like being able to understand why it's correct.
Right, exactly, right.
How do you go from there could never be more than 21 million? Like, what is like that's like the headline, but what is deeper down into that specification that you would start to break that problem up into?
Yeah, so first we have to come up, like, what you're kind of asking for is like, what is like the constructive architecture of Bitcoin, right? So you might start with, the thing that I started with at least was compact size. So in the Bitcoin protocol, there are all sorts of situations where you need to send out lists of things, TX ins, TX outs, the number of transactions in the block itself. Like, so in a block, there's a list of transactions. How do you know how long that list is? Well, there's this thing at the beginning called compact size, which tells you how many transactions you're going to see later in the block. This compact size is, what it is it's a number that can either be 1, 3, 5, or 9 bytes. And that it was like the smallest structure that I could start to like work with. And then so I started to do things like, okay, well, for every compact size, an encode after a decode would always, I'd have to prove, like, I'd have to pull up the actual code, but there are certain things about like the decode encode round tripping. So if you have something and you encode it and then you decode it again, that you get the same thing back. And then there's like the other version, which is that if you were to pull if you were to start with decoding something off of the front and you were to re-encode it, it would give you the exact bytes that you pulled off the front of the byte stream.
So decodec and codec code.
I don't know exactly what you mean by that, but yes, there's this dual inverse property of the encoding of the compact size and its like abstract number. You know, there's also like a really boring theorem about compact size would be like it never takes more than 9 bytes when you encode it. I'm glad that you said that. This repo is not in the business of shoulds, period. It's not, its goal is not to make normative value judgments about how Bitcoin should work.
It just does.
It just does. Now, that might be a useful claim later because then we might say like, okay, for instance, there are only like, because of the way that compact size works and because maybe it appears in like the block headers and stuff like that, that we can then say like, okay, block headers are always exactly 80 bytes. And that might be useful because like now we can make bounded claims about how long the blockchain is when we are considering only the headers. And that can be useful. And this is actually my whole goal with this entire project, which is that I spent years embroiled in debates about, you know, check template verify and like whether or not certain things should be added to or removed from Bitcoin. Like, should we change this about Bitcoin? And those should discussions are very good to have. But if you've ever participated or witnessed the way that Bitcoin development happens, it's not always clear whether it's a civil technical debate or a sort of politically charged debate about these things, or like about like values. And so the whole purpose of this repo is to sort of take out all of the like rhetorical nonsense that happens in these debates and just point to something and being like, hey, if you do this, this will happen. Now, whether or not the result of this is something you want or not want, that is a value judgment for you to make. And everyone will make their own, and like that, there's plenty of good discussions to be had. But sometimes people will make claims like, oh, if you do this, then this will happen. And that if-then statement itself is false. But it's like not always easy to tell that it's false. So it's helpful to be able to point to something that proves one way or the other how the system actually works, how hypothetical changes to that system would change the properties thereof. And then you can get to the starting line of having these values-based conversations. Yeah, and so that's why it's very important to formalize the protocol as it is. And it's also really, and one of the important parts of this work too is trying to separate out what is like kind of a very like embroiled thing, which is like, what is the Bitcoin protocol and what is the Bitcoin core, the implementation? Because especially when you start to have things like BTCD or libBitcoin or like other alternative Bitcoin implementations, you know, some people will be like, well, core, like the spec, the code is the spec, is something that people will say. So like they're tacitly or like implicitly giving Bitcoin core this like this legitimacy or this like power to dictate what the protocol is. And I believe personally that that is cope for just not having a good specification for what the protocol actually is. Now, if we have a good specification, then we can say, well, this is what the protocol is, or this is what we think it is, and here's a proof that the Bitcoin core implementation satisfies that specification. Then you can also say, like, oh, now my new implementation also satisfies that specification, even though it differs from core in the way that it works. All of the properties that we care about are satisfied by both implementations. And so it can give you more confidence in running alternative implementations. It can, and then I think one of the cool, one of the best case scenarios for this project that I'm working on, if it succeeds, what it could give us is a formally verifiable like consensus library. You know, people have talked about libBitcoin kernel forever, which is this idea of extracting out the consensus code of Bitcoin into this tiny library, because Bitcoin core is so many things. But like there's the tiny consensus library that everybody is like shit scared of like making changes to, and rightfully so, because that changing that can result in chain splits, and now that nation states are involved, that can result in war. So it's like very, very useful to be able to extract that out and to also understand it very deeply.
And even worse, it's written in C++ from like multiple decades ago.
Right,
So,
and everybody's afraid to touch it.
yeah.
Right?
Yeah.
So it's like not only is it old, but it's the thing that people are most afraid of improving. And I would say improving even in a semantics invariant way. So I don't mean making changes to consensus. I just mean changing the code so that you can clean it up around consensus. People are like very afraid to do that, and again, rightfully so. But tools like this can give significantly higher confidence about making those changes, and it can then also distill a lot of the collective knowledge we've built up as an industry about how the protocol actually behaves.
Similarly, the one time in Bitcoin's history where we changed from one embedded key value store to a different one was a shit show. Like,
Yeah.
there was consensus failures from when we went from Berkeley DB to Level DB. And I'll be honest, pretty much every embedded key value store I've ever touched, I hate. I hate LMDB, I hate Level DB, I hate Berkeley DB, I hate RocksDB, I hate anything based on log structure merge tree. Like, it's just all of it sucks.
But what's interesting about this, right, is that all of those are just implementations of key value stores.
Yeah.
So if you had an abstract definition of the properties a key value store is supposed to give you, then you could say, assuming a good key value store, all of these other properties hold. And it's left as an exercise to choose the right one that actually satisfies those properties. And then you can start to have arguments that are like separating out the different things. And this is done informally all the time on the Bitcoin Dev mailing list and on Delving Bitcoin and like in various BitDevs meetups around the country and around the world. But it is the merging of a technical and a like charisma game, right? And I think Bitcoin does a generally pretty good job of trying to keep things mostly technical and like mostly meritocratic. But I think one of the things that you'll learn is that the better your proficiency in the the tech of these discussions, the more you'll see how much influence some of these charisma games play or these clout games play, like where certain people are given more deference to when they say something, even if they might say the exact same thing as someone else.
Well, that's one of the reasons why I've gotten very interested in Lean 4 proving. In addition to the fact that Grok 4.5 is also quite good at it. I have about probably 50,000 lines of Lean 4, just it's spat out from like the past couple days it's been out. I've been working on 3 different projects right now in Lean. I'm curious, like, if you might be interested in any of those. I don't want to like derail it though. If you have more you want to say.
Well, let me get to a couple more broader points, and then we can sort of retire the main discussion. The thing about this that is really interesting in a post-LLM world is that if you know anything about LLMs, a lot of it is like next token prediction, right? It's like, given this context, predict the next word, predict the next word, predict the next word. And so the interesting thing about something like Lean 4 or even Coq or like other proof assistants that are tactics-based is that a tactic is a way to take a claim that you're trying to prove, sort of make a move in that proof, and then it gives you a new proof state to try to prove thereafter. And so it lends itself very well to this tree-like exploration, where I'll predict the next tactic and it gets me down the tree a little further to like closer to the thing I'm trying to prove, and I do that all the way until A equals A, reflexivity kicks in, and you're like, okay, cool, this thing is proven. And so it means that the structure of tactics-based proofs lends itself very well to next token prediction, because next token prediction is also next tactic prediction, and then you can, it's organized in a data structure that's very easy for LLMs to learn. So that's one thing that's really nice. The other thing that's really nice is that the signal that it gets for whether or not it did the job it was supposed to do is really clean. It either, the proof checks out or it doesn't. There's no like, oh, the software runs, but it does the wrong thing. Or I didn't implement the part of the test suite that like checks for the thing that I actually care about. It's like, no, it either passes or it doesn't. So not only is the proof language or like the corpus of data of these proofs lends itself very well to be learned by LLMs, it's that the entire process also lends itself to being learned by RL training harnesses. We were talking a little bit about this at the beginning, but the RL training harness is basically saying, like, here's the problem statement, come up with a solution, now check if your solution satisfies the problem statement. And then just do that in a loop. And if you're wrong, you'll kind of like get nudged away from what you just did. And if you got it right, then you'll get nudged towards what you just did. And so because this reward signal is super clean, it actually gets really good at writing this stuff really fast in ways that it will, even though there's like probably orders of magnitude more Python data out there or JavaScript data for these LLMs to learn from, like Lean is like a very, very small training data set. Yet it will learn from that data set far faster because the structure, all of the structure that's embedded in that data set is extremely learnable and extremely clean. And so I expect that, you know, for all languages right now, LLMs will continue to get better, but the slope of improvement for these more precise languages is going to be much higher. So it's going to get much faster. It's going to learn how to write good Lean 4 much faster than it'll learn how to write good Haskell, then it'll learn how to write good Rust, then it'll learn how to write good C++, and it'll learn how to write good JavaScript. Those slopes are kind of like shallower and shallower as you move across that.
So you believe that there's going to be a bit of an asymmetric advantage in doing previously considered difficult things by proving that you can do them in a way that works well, and that proving capability when augmented with LLMs will essentially generate a data corpus that could then be used to almost recursively improve the next models. Yeah.
Yes. And that is the hypothesis. That is that is the thesis that I'm betting the next decade of my career on.
I think that's a safe bet, dude. I mean, are you finished? Okay, so I want to go into like some of the stuff.
Well, I want to also like get questions. So
great.
I know that.
For sure.
Yeah.
I might have missed it. Okay. It's nothing big. I mean, I might have missed it earlier, but Lean 4, is this a new programming type, or is this something that's older that's being used now?
So Lean 4 itself is new, but theorem provers in general are not. So remember how I was talking about languages versus clusters? The cluster is old. The specific thing in that cluster is pretty new. The reason that it's the one, so you might ask the questions like, well, why not use one of the older languages in that cluster? Like, what's interesting about this new one? And it happens to be this weird accident of history that right now there's this massive effort going into formalizing all of undergraduate mathematics as a single library in Lean 4. And this has nothing to do with Bitcoin. This is like a bunch of people who got really excited about the incremental improvements. And they're subtle things, right? They're not groundbreaking improvements. Like Lean 4 doesn't have groundbreaking improvements over something like Cocker Isabel. But it has a lot of ergonomics improvements that make it really nice for mathematicians to do mathematics work in. And as a result, the same way that like Python has a shit ton of libraries for just about everything because it just happened to strike the right balance of like usability and like the fact that it like an actual good tooling maturity. That's what the mathematicians are getting out of Lean 4 right now. So now all of MathLib is being built on Lean 4, and that means that for any type of proof that you wanted to do, you can just invoke any theorem in mathematics that has already been proven and just like import it the way that you would import a Python library. So you're like, oh, I want Lagrangian interpolation, which is like how like zero knowledge proof, things like Shamir secret sharing or like polynomial commitments from zero knowledge proof stuff, like all of that hangs on Lagrangian interpolation. And it turns out that that's just a thing in a library that mathematicians already defined in Lean 4. And so you just import it and just, you're on your merry way.
Do you think that that gives it an advantage as a language over other languages because of the mathematics of the language? Or is it just...
It gives it an advantage. I don't know that it's the, like, I think it would be silly for me to make the claim that Lean 4, like all software is going to be written in Lean 4 in like 2 decades. I don't find that to be realistic. But I do find that because all this is getting easier, the threshold is lowering for when you might try to cross into using one of these things. So right now, you might only choose it for like super, super high stakes projects, like trillion-dollar assets, rockets you might launch into space, you know, banking, automotive, medical, like these like things of high consequence when you get them wrong. But there's a threshold of what high consequence means, and I think that this just structurally lowers it. And so a whole lot more things are now going to become viable for that. And so I expect to see a lot more things that would normally not get written in Lean 4 to get written in Lean 4 simply by virtue of LLMs changing the cost structure of its implementation. Yeah.
Yeah, mine was, when did you start your project, where you currently sit, and not to put you on the spot, but is there a forecasted or targeted finish for your project?
So I've been working on it for about 2 months now. What was the second part of the question?
When you started, where you're at, and if there is any kind of forecasted or targeted completion.
So let me answer the last one first. Targeted completion is not, I think, the way that I think about this. I think that it's going to just be a growing, like, I might misuse this terminology because I'm not, like, I don't have, like, Jewish relatives, but, you know, like, there's like, the Torah and then, like, the Talmud, right? There's, like, this entire huge scholarly, like, sort of interpretation and understanding, and it's, like, constantly growing. That's the way that I kind of see this. I kind of feel like it's, like, the Talmudic base of Bitcoin, whereas like the actual code that we might run is like a much, much smaller set.
Well,
and so I do expect it to grow sort of unbounded, but I do think that a lot of the value is going to come like in sort of this like earlier section, and then it might grow in the direction of like maybe we formalize Lightning next, maybe we formalize BitVM next, maybe we try to use it to describe like different hypothetical extensions to Bitcoin script. Right? It ends up being a tool that is an ongoing helper of facilitating Bitcoin development. And so I don't see it as complete. But that said, I do have a set of milestones, and each one of those milestones do have like completion criteria. So like the first one is being able to specify fork choice rules. So like what constitutes a valid Bitcoin chain under consensus, and within the set of valid chains, what is the definition of the canonical chain? So highest proof of work, right? So like that would be one of the milestones. You know, another one might be like, can we get a formalization of Bitcoin script itself in there? Stuff like that. There was a second thing in the middle. Where do I sit? I'm not done with that. The first thing that I'm really after in terms of like headlines is that fork choice thing. That's not yet done, but I expect to have that done before the end of the summer, and that's a very sort of conservative timeline. I'm routinely surprised by how much I can get done by myself with Claude. So.
I thought you were using Claude and learning so much right now. Claude's the only LLM written, I mean, outside of open source that you should be using coding with. At least that was the
I don't know. I find that Claude is much better for. Claude's a little bit like it's too like put me in coach, right? Like it's very eager. That helps sometimes because it sometimes spot checks and like thinks about things before I see them, but it's much worse than like Codex at like sticking to a task. If I have like a high precision thing that I just want you to like just do it, don't do anything else, and do it exactly right, like I want to hand that type of a task to Codex typically. And Claude, it's more if I'm like building stuff greenfield from scratch. Like I find that Claude does that better than Codex. So when I say that, what I'm specifically referring to is Opus 4.8 and Fable 5.
Yeah, nothing other than that. I haven't even touched Fable yet. Yeah, it's free right now, I think. I am gonna make a statement to you as it relates to like what you're doing in terms of quantum protection and what he's doing. Like it's more of a statement, and like I feel like maybe from what I've learned about what you're building, like you're doing would be like we are really so early. Like what you're doing is building a validation set for Bitcoin. At the very base level, and that validation set will help on some level with
Yeah,
cybersecurity protection.
the work that I'm doing in theory at its best could accelerate the BIP 360 sort of like from where we are to like full activation. Not directly in the sense that it doesn't give BIP 360 like implementations or rules or anything, but it's more to like help settle disputes between people who are arguing about different ways to design BIP 360, right? Or like the implementation thereof, right?
But this would be a standard set moving forward across chains if people wanted to apply this.
I mean, across Bitcoin forks, yes, it could. It's not realistically going to be useful for Ethereum because Ethereum is like, it's different at such a small level that you could learn from the approach, but you're not going to get anything out of like the actual like corpus of like proof statements.
So like if there was an interloper and it wasn't validating against the data sets as described in the protocol, that would immediately be like sort of a defensible, like that's how we would identify.
So consensus already works like that. Like it already implements a whole bunch of checks. It's more if, for instance, we wanted to say like, oh, I want to implement this soft fork. And I believe that this C++ code is actually, that's actually a really interesting one, right? It's like, hey, I have this BIP. It's proposed as a soft fork. Here's the C++ implementation of it. There's a question of like, is that C++ implementation actually a soft fork or is it a hard fork? Like, you could squint and like most experienced developers will like make a judgment call and they'll probably be right about whether or not it is a soft or a hard fork. But like sometimes you end up with either bugs in the implementation or edge cases where you have like two separate proposals that like when they combine in a weird way, it ends up with something that you didn't expect. So it can help identify and settle those types of things.
Yeah, well, like BIP 360 is actually a really good example because one of the problems we had in BIP 360 was we wanted a Merkle commitment of different possible spend paths that you can pick at spend time. So if fees are high and you really need it mined soon, you'd want to pick a shorter algorithm that might be a little less proven, but like you'll go for a ski sign or something like that, or MLDSA instead of SLHDSA or something like that, right? So like you'll be able to pick what you want to spend so long as that's active on like it is something you can spend. Now, having this like multi-algorithmic agility built into the Merkle commitment, that's useful, but then you run into a problem where you're essentially basically overwriting 6 new opcodes for every new algorithm you add, because you need opcheck sig, opcheck sig verify, opcheck like tweak add, and various other things, right? So like you're basically rubber stamping that out over all the taproot opcodes, and you can keep doing that if you want. It just seems not great, and maybe there might be a case to be made for operator overloading of the existing opcheck sig opcodes if you can find a way to do it safely, and if you can prove that. And so that was one question I'd like to prove using Lean. And if we can we do it without needing to add any additional information? Like before we had lean provers, we were thinking, well, maybe we need to include what I called a flyleaf byte, an extra byte that would have some bit field or compact size encoded bit field that would essentially allow you to disambiguate which specific algorithms you expect to spend in this tap leaf. And then you would also like, it's just like, it's like, okay, does it work under multisig? And if so, under what conditions? Like, are you assuming that we're not going to have multi-algorithm homogeneity in the multisig itself? There's so many like different like little rabbit holes and like questions that if you could just prove that formally, then it puts the question to bed, and we might not even need an additional like disambiguation byte that helps with that interpretation.
I think if we could sum all of this up, the usefulness of this type of work is to answer the question, if I make this change, is it gonna fuck everything? Like, being able to reliably answer that question is like super useful.
Super useful, yeah.
Yeah, I still think we probably will create more efficiencies within the block time itself.
I mean,
Well, that's
very indirectly. Very indirectly.
It could definitely make the node implementations more efficient because
they're gonna have higher confidence in making changes to that sort of thing.
Because like even right now, like when you do an IBD on a node, it does not take up your full machine's resources. Like you really have to like either run it on a very weak machine or like it's just there's this global lock called CS main that I hate. It's because it's always locking, like it's just getting in the way of it being the most optimal use of the system resources, using all your cores and all your RAM and all your bandwidth. There's CS main is one of those. There's of course the performance of SecP v6K1. CS underscore main if you're looking, yeah. And then there's also like another one is level DB is just like all of these embedded key-value stores, they have these limitations that are really annoying. And that's why I developed an interest in Lightning Memory Map DB, and I was thinking, well, why don't we just drop this into Bitcoin Core? And like, so I had like Grok, like vibe code, like, let's try it out, right? And when I did that, it was so much worse. It was like, wait, why is this worse? Well, turns out it has this single writer limitation. Where like you can have multiple readers. It's really good for like, concurrency and parallelism sort of reads, but writes are very much bottlenecked. And so like, okay, well, you'll just, have a separate database for your UTXO set as you would have a separate database for your, whatever else you're doing with level DB in the context of like, are we putting, what are we putting in there? Like UTXOs from, before stamps or inscriptions, like after, are you making buckets? Like how are you trying to be more strategic? And unfortunately, it's just not that helpful. And so one of the first things that I started doing in Lean was I was like, you know what? I just want to prove some of these KV concepts, like multi-writer, and figure out like, at what part does it become difficult to atomically and reliably, preserve like, your atomicity, consistency, all of those like, durability, all of those sort of like
acid guarantees.
Yeah, exactly. Your acid guarantees, and then while still also like having, a scalable way to fully utilize all of the machine's resources. I mean, modern day SSDs, like even NVMe 4 is like blazing fast, and we're just not using all of that bandwidth as we go to want to persist in-memory data to disk. And you can talk about like a write-ahead log, a pen only. You can do things like, compaction, and you can have log structure merge tree approaches, and then you have this extra process that's always just like kind of, trying to balance things and make things more performant over time. But like the problem is like it's just all of it, none of it's ideal. And I haven't found an embedded KV store that makes the full use of your system resources when it's at maximum contention. And so that's like the first thing I thought of doing with Lean. And then the second thing was like, I saw your project and I was like, you know what? You don't have SecP in here yet. I'm gonna see how hard it is to prove SecP. Turns out it is, dude, I probably have about 5 times more Lean in my SecP stuff than you have in your BTC verified repo. And I think it's because we're solving different problems in different ways. But, and also I can't tell you if the Lean is any good or not.
Well, that's the other thing is I have a very high touch approach to my stuff, right?
Yeah.
Like I don't like, especially when you go from like a constructive bottom up thing, small errors in the way that it makes decisions about how to formulate certain things at the bottom can like accrue and compound on the way up. And so I've taken great care in sort of only going incrementally. And I have the benefit of like kind of understanding Bitcoin kind of all the way down to like its bedrock. And so I've just been trying to like build it up incrementally from there. And that's why there's like a lot less code. It's also because like I'm only at the level of syntax right now. Like if I'm kind of, you know, bending some of these terms, but like if you think about the Bitcoin protocol, there's the syntax and the semantics. I like was working on syntax basically for the last 2-ish months, or like, you know, the prior 6-ish weeks, and only just started on semantics in the last 2 weeks. And semantics is actually a much larger share of what's going on.
Well, I applaud that effort, and I'm happy to support it however I can, and sort of like getting into the more the nitty-gritty of things. I'm finding like, I'm trying to figure out if Lean is any good, and I haven't proven that yet. If it's any good at like good enough systems programming, like to be at the point where it can essentially be essentially the implementation would be essentially informed by the C-generated code from an AOT ahead of time compiled Lean 4 spec.
I think, yeah, so
Or proof, I should say.
the success of my work does not depend on the efficiency of the extracted code. That would be a huge, nice to have, but I would say that this is independently useful even if the
Without a doubt.
code that you can extract from it is dog shit.
For sure.
Yeah, so Lean, and Lean's not the only proof assistant that does this, but like it has a heavy focus on C program extraction. So if you write a bunch of Lean code that like implements, you know, this, that, or like say, there is actually an implementation of SHA-256 in my code base right now. You could, like SHA-256 is implemented in Lean, but then you can then say like, you can give the compiler some extra arguments and it will extract C program that implements the exact same thing with significantly higher guarantees that that C program has the exact properties that the Lean, the Lean propositions and proofs assert that it does. Because like otherwise you run this risk of like, okay, you have this elaborate set of Lean code, you have all these proofs about it, and it's like, okay, cool. Now we need it to execute in Silicon. What now? So well, you could implement all of what you did in Lean in C, but then how do you know that the C code that you wrote matches the Lean code that you wrote? It's really like that ends up being like a risk factor in the translation. And so the nice thing about having that embedded in the compiler architecture itself is that you write the Lean code once and it extracts the C code, and that translation itself can be formally verified.